Hey everybody, it's Beej with Lambda School. Today we're going to be talking about graphs, sort of an introduction to graphs and what they are, what they're made of, and what they're good for. So what we've got here is a simple graph in computer science. It might not be like the graph you're thinking of immediately. I know that in Lambda School we've talked about graphs before in the past and how to build simple graphs, but we're going to tear into that a little bit more here. So in the introduction to graphs, we want to know what graphs are and what they're made of and what they can represent. Let me show you a simple graph here. And it's actually not entirely simple, but what we have is a graph here that's made up of edges and vertices, and the edges connect the verts together. And also here we have a weight associated with each edge, and these numbers and letters, we'll just call them the names of the vertexes. This is a graph that represents something. I'm not quite sure what, but here's a graph that represents something else. This is the ARPANET map from 1977. So this is the internet back in the early days. And here we see the nodes represent locations and computers, and the edges connect these locations together, probably with what was at the time very high speed connectivity, probably 56 kilobits or something. Thankfully, we've come quite a long way for most of us who don't have DSL in the middle of nowhere. So what else do we have? Here's another example of a graph. This is the London Underground map. And we have nodes here, and we have edges connecting the nodes. And if you wanted to get from one place to another in London, you would look at the vert that you were at and the vert that you were going to, and you would draw lines from the connections, the edge connections, to get to wherever it is you wanted to go. Here's another example of a graph. This is a graph that shows people and friends on a social network. So it's really hard to tell here, but if you follow the lines from one person to another, you can see who is connected to whom. There's another graph, a directed acyclic graph. We'll get to that in a second. So what can graphs represent? We've talked a lot about this here. One other thing that I could mention is a collection of cities, where the vertexes are the cities and the roads are the edges between the vertexes. We saw a social network example, but it could represent pretty much any kind of network of data where you have one-to-many relationships between different types of data. Some quick definitions here. Undirected and directed, cyclic and acyclic, and weighted graphs. This graph will show a whole bunch of these things. So a directed graph is a graph in which the arrows have directions. So we have an arrow here. This is a one-way connection. You can think of it as a one-way street. If these were cities and these were roads between the cities at the edges, then this edge would be a one-way street. Sometimes if you have two-way streets on graphs like this, you represent it with two edges, actually, two one-way edges. Like here, this edge that has weight 2 and this edge that has weight 6, these edges form a two-way street together between the verts labeled 1 and 4. Cyclic and acyclic. Cyclic means that the graph can form a cycle. That is, you can follow a route over and over again like a race course through the graph. So here, this is definitely a cyclic graph because it has cycles you can form. For instance, we can go from 1 to S to 2 to 4 to 3 to 1 to S to 2 to 4 to 3. We formed a cycle there, and there are even more trivial cycles between 1 and 4. There's an immediate cycle right there. So this is a cyclic graph. And the other thing I mentioned was weighted edges. So here are some weighted edges on the graph. This edge is weighted 10, this edge is weighted 2, and so on. If this were a graph that represented cities and roads, these edges could very well be the distances or the lengths of those road segments. And if you wanted to move from one city to another, and then to another, and then to another along the graph, you could figure out the total length of travel based on those road segments. Sometimes the weights are used in other ways. They can be modified to change how much it costs to take a certain path along the graph. For instance, one thing we might do if we're doing a map of how to walk from one place to another destination, walking directions might be very different than car directions. For example, the car directions may say to take the freeway because that's the most efficient. But if you're walking, you don't want to take the freeway. And so what you can do for a walking graph is you can say, hey, is this edge a freeway? If it is, go ahead and multiply the weight by like 1,000. So now the freeway comes across as a very heavyweight, very long, artificially long freeway. And as such, when you were doing routing to walk by foot, you would never choose that direction because it is so much heavier than the rest of the weights. So that is what weights can be used for. There is a special type of graph called a directed acyclic graph that I wanted to mention. It has a lot of uses. And what this means from our previous definitions, one, it's directed. So there is a direction for each edge. They're not bidirectional. And it's acyclic, meaning there are no cycles at all. And I have an example here of a directed acyclic graph where you can see once we arrive at, say, this node here, this vert, there's no way to get back there. There's no way to form a cycle. And this is true for all the vertexes in this graph. There's no way to form a cycle to move backwards to where you were previously. So let's do some stuff together here and draw up some sample graphs. So let's draw some examples of directed and undirected graphs, some examples of cyclic and acyclic graphs, and so on. And I'm going to use a handy-dandy drawing tool here, which does have the drawback of not being able to draw undirected edges. So normally, if we've got two vertexes here, and we were drawing an undirected edge on this graph, we would just not have an arrow. There would be no arrow associated with it. It would just be a single line. But in order to show that this is bidirectional, let's put another edge there. So this is a directed graph because it has arrows. Again, if we wanted an undirected graph, we would just draw a straight line here with no arrows on it. And this is a cyclic graph. We already know this because it has a cycle in it right there. No matter how many more edges we add out here, we will still end up with this being a cyclic graph because you can form that cycle right there. But if we wanted to make an acyclic graph, if I just merely delete one of these edges, then now it is acyclic, right? There's no way to form a cycle in here. There's no way to get back to a node or to a vert that we have previously visited. So there's an example of cyclic and acyclic graphs. Let's think a little bit here briefly about how we might implement this, and we'll do this later on in class. How would you actually implement a graph? What kind of data structures do you need to represent it? Well, we know we have vertexes and we have edges, and each vertex seems to have an arbitrary number of edges associated with it. So what kind of structures might we use to represent this? Something to think about that we'll talk about later. Let's see here. Directed, undirected. One more thing to point out about graphs here before I turn you loose on some exercises to try. Note that a graph is actually kind of similar to something that you've seen before. If this looks at all familiar, I've drawn a binary tree. It's very similar to a graph indeed. In fact, a binary tree is a special case of a graph. It's directed, it's acyclic. It also, trees tend to have the concept of something being a root of the tree, whereas graphs do not have the concept of there being a root. And of course, this is a binary tree, and graphs can branch out as much as they want. Although technically this is still a tree, we're just not a binary tree anymore. And graphs really start behaving strangely compared to trees when you start having connections like this, or you start having connections like this. So graphs give you a lot more leeway of what you can represent and what kind of connections you can have between different vertexes on the graph versus a tree. So what you should do now is check out the exercises at the bottom here. Go ahead and just hand draw these things. Go ahead and make up what they look like. I give you a vertex count, but just to make sure that you have an idea of what these types of graphs look like. And then next, we will talk about some of the basic algorithms that cover what you can do with these graphs. So have fun, and I will talk to you shortly.